Hello, everybody. My name is Lewis. I'm a fourth year PhD student in EC department at Professor Kalmberg's lab. Today, I'm going to cover the basics of analog or digital circuit layout. So first of all, let me quickly introduce what is layout. For those who already know how to do PCB design, layout is nothing but using what you already built in a schematic and put them into a physical implementation. And basically, you're designing with the transistors that the PDK provides, the metal stack that the PDK provides, and you're basically putting everything from smaller pieces from transistors into your system. So this is the part that your electronic design in the schematic actually gets into the circuit level. And once the ideal workflow is that once you're done with layout, you would do post-layout extraction because there will be parasitics introduced during your layout process. These parasitics may involve parasitic capacitance, parasitic inductance, resistance that could degrade your circuit's performance. So basically, after layout, your circuit's performance will degrade or change at least with respect to your schematics design. So that's why after you lay out, ideally you need to do post layout extraction and then run it again, run the simulation again, make sure everything is correct, and then you can send the layout to the foundry, for example, TSMC, global foundries, and to let them, and in our case, I guess it's SkyWater's, to let them manufacture the circuit for you. So if you look at what's shown on this picture, this is the, I guess, cross section of a real chip, a real taped out chip. So this is a separate process. This is called SOI. This is a kind of a very interesting process, but we'll ignore it. And for basically for all the taped out chips, if you cut the cross section, it will mostly look like this. So on the bottom, these are the silicon. This is the silicon dioxide for insulation and whatnot. And then if you see up here, these Lego-like ladders, this is the cross-section of the metals that you build in circuit. So these, if you think about them, these are literally just metal strips laying on top of each other. From metal 1, metal 2, all the way to, say, metal 5, metal 7, in this case. And then if you look at this picture, this basically shows well in the layout view of in a certain schematic. So you have your transistor here, source, gate, drain, and then you would need to put them into this fashion, draw that into this fashion, and once you draw it like this way in the standard way, you send it to the foundry. They're gonna make this for you. So now let's hop on to in our case, how to lay out a simple inverter, or in this case, I guess it's a. This is an example with the common source amplifier. So we have the circuit here, and this I'm showing here is what I previously laid out, a clean and finished layout of this cell. You have your NMOS, which lights up here, PMOS lights up here, and then your NMOS lighting up here. And then all these different rectangles, they are actually metal traces that runs through, that connects the individual nodes together. So with that, let's go to this layout, and I'm gonna do it step by step and show you guys how to do layout. So what you do once you have your schematic ready is you do launch, and then you do layout Excel. You say you have create new, automatic. This is all good, all good, and then bam, this is gonna pop up. So this is a good way that you I guess put your different windows together, because on one side you can see your design, and on the other side, this is the window that you can do actual layout in. I would strongly suggest people start using a mouse for the layout process. As you may have noticed, right, drawing schematic with your touchpad is already very hard. For layout, I would really recommend using a mouse because the clicks are going to be easier. Moving things around will also be easier. So first thing that we see in this window, in this actual layout window, is these layers, valid, used, routing. So right now with valid, these are all of the layers that the Foundry, that the SkyWater PDK provides us with. So all these are the available layers that we can draw on. They have different functionalities, but usually, most of the time actually, we don't use all of them. And if we do used here, this is basically selecting everything that is currently used in your view. And because we haven't created anything yet, that's why this is blank. And for routing, this is going to only leave the routing layers. So here you see Metal 5, Metal 2, so from all the way from Met 1 to Met 5. And down here, this is the poly, this NPC. These are the doping layers and and some poly resistors where you can make it here. Yeah, and then if you check all of them, this means you're having both not only valid and used, but also routing, because again, we don't have anything here. Nothing shows up. Okay, so I guess the first step that we need to do is how do we import the designs that we have in the schematic first here. So one way that I guess in the 80s or 90s, what people do whenever they want to draw layout is that they have to draw the doping sections, the different diffusion layers and everything manually, which is very hard for today with circuits and billions of transistors. So instead, one thing very quickly we can do is we actually can just automatically import all these transistors into the layout view. So what I prefer to do is I would just select each one of these transistors. By the way, you press on Shift while selecting for multiple selections. And then you would you have this button here that says generate selected from source. So if you click on this, you see that the two implementations of the transistors already show up on the screen, and it moves with a mouth where we can place it anywhere. And I guess also another important thing to notice is for drawing layout, you need not only your mouse, but also a lot of these short keys are also very helpful. So for zooming in, you just need to scroll up or down your mouse or your touchpad. But then if you want to just center your design, you would just press F. So press F, it's going to just automatically center and zoom in to all of the things that you have. Let's say you have in the other example, if I have another transistor here, right, if I put them like this and I press F, it's just going to zoom into the section that all of your implementations are in. So let's take a look at these transistors first. So this, as you see, this is the PMOS, this is the NMOS. So for the PMOS, because we imported the design from the schematic, we have the source as VDD, bulk as VDD as well, which is this guy, and drain as out, which is this guy. So you see everything here, the net also corresponds to what you implemented in the schematic, which is very helpful because you know which wire goes to where. Same thing for the NMOS, right? But you see that there's actually no connections so far. There are nowhere that we can place our metal layers. So what you need to do is actually, although in some other PDKs, this process is actually automatic. In this case, we actually have to do a tweak a little bit. So if you select this transistor and then if you press on Q, which is for property, the same thing as in the schematic, you see this window popping up. And then in the parameters, you see the gate connection, which is currently none, right? There's enable M1 to MCON on source and drain, so SD means source or drain, and the tabs. So let me explain each one of them one by one. The first is for gate connection. Right now, as you see, because of the way that we generated or we imported the transistors, there's currently no gate connections. So what you need to do is that you need to enable them currently, which is none. You can either do top, bottom, or both. So if you have both, you'll see that these two guys pop up. These are the these are the gates, right? Which is noted as input, the in node, which is here. Uh, same thing for the uh, so, so, same thing for the enable M1 mcon on source and drain. So right now the source and drain, they're just buried in there. You don't have any connection or tabs that connects to M1, which is metal one. So you have to enable them. You have to check this. So once you do it, you see something changed a little bit, and then you see this blue color, which is actually the metal one. So now it does have metal one on it. You can connect it with the metal one to wherever you want. Finally is this tab. This tab basically means this bulk tab. So by default, it's also disabled, and you can either put it to the left, which is like this, or to the right, or I think you can actually get both. Yeah, but most of the time this is not necessary, and I would just leave this as top for now. I guess you have to play with these parameters before doing layout, because these are the transistors, which is, I guess, the foundation of how you're going to route things. But then even before you play around with these, you have to think about how would you like these transistors to be connected. How would you picture your overall layout is going to look like? So, because in our case we have a very simple inverter, and with PMOS on the top and NMOS on the bottom, we would try our best to make the area after layout as small as possible. So one thing we can do is that, and if you noticed, we have the gate of both PMOS and NMOS shared. So what I would do is that I will merge the gates of the PMOS and NMOS together. So what I'm gonna do is I'll put gate connection to just top for the NMOS, and I'll have, of course, you have to enable the connections on the source and drain, and then I'll leave the bulk tab, which also connects to VSS here, or ground here, to bottom. And I will try to make this PMOS symmetric to what I did to NMOS by putting gate connection to the bottom and enable M1 con on the source and drain, and then I'll have the VDD tab, the bulk tab, on the top. So everything looks very symmetric here, which is good. And the next thing I'll do is to overlay the gates of the PMOS with the NMOS, because they're the same net, right? So what you can do is, if you press A, so A stands for aligning, which is a very cool tool. If you press A here, and basically for this A tool, you should look it up on Google on exactly how it works. But I can show you that if you click on one node here on the first thing that you want to move, and if you click on the second thing, it's gonna just move them together. So what I did just now is that, let me try this again. I press A, and then you can either select a node, which will light up as this, or you can select the edge for alignment. So if I select this edge, and then if I select this edge, these two edges are gonna be aligned or connected. You should play around with this because it's a little bit hard to explain in a video, but you'll get it very soon. But always remember that press A, and then tap on the first thing that you want to move, and tap on the second thing that you want to move the previous thing to. So here I want to just overlay the gate connection of these two transistors. So what I would do is I press on the center of the transistor that I want to move, and then I press the center of the transistor that I wanted to move to. And there you go. The PMOS and NMOS, they're merged on the gate. So another important thing that we need to remember is for M, which is, I guess, same thing in schematic, is if you press M for moving. So if I first select this transistor and I press M, I can tab on it again, and I can move it in these directions. There's this clever button of F3 that gives you the additional settings for all of these commands that you're putting. So if I press F3 here, you see that this is move, and the snap mode is orthogonal. That's why I can only move in X or Y direction. If I put it to any angle, I can move it anywhere, but it's quite not convenient, and you can see any other things. So always remember that for any command in layout, there's always an F3 for more selections, more properties, I guess. So even for A, for example, if I press A, and then if I press F3, there's like snap targets. So right now it's edge and points, meaning that you can select either edge or points, or you can just exclusively select one of them. There's also an offhand and whatnot, which you can experiment on your own. So again, I selected the center of the gate of the NMOS, and then I move it to the gate of the PMOS. So right now these are moved. These are connected. So now that we have a view of what we're going to route on the transistors level, we have to start thinking about how do we route the metals together. So if you look at the connections that we have here, what are the connections that we need to make? So we need to connect the bulk of the PMOS to the source of the PMOS, which are both VDD, and we'll need to connect the drain of the PMOS down here, right? So because the current flows from the source to the drain for the PMOS, going down here to the NMOS, and then flows from drain to source. And yes, and also we need to connect the bulk of the NMOS to ground, which is also the source of the NMOS. We don't need to worry about the input anymore, because although the input, which is the gate connection of the NMOS and PMOS are together, we just did it, right? Because we just merged the gates together. So we don't need to worry about it anymore. Okay, so before we proceed to actually making the connections in metal layers, one thing I would suggest is to turn on some of these DRD buttons. So if you have here DRD notify off, you should press on it, and now it says DRD notify on. The other thing that I would suggest is DRD post edit off. You turn it on to DRD post edit on. So what DRD means is design rule direct or something. Basically, it's gonna in real time check if your routing violates with the design rule. So there's this thing called DRC, which we'll need to do after we do layout. Basically, it checks between your schematic and your, so that's LVS. So for DRC, it's basically checking your layout standalone. Does it match with what the foundry can fabricate, right? If you make something crazy, let's say you draw a line of 1 nanometer, right, in this 130 nanometer technology, the DRC will yell at you saying you can't do that. We can't make it for you. This is a violation. But running DRC takes extra time, takes extra effort. So that's why here we prefer to have DRD, which is real-time rule checking, to be turned on. So we have notify on and post edit on. And if I make some weird mistakes later on, you'll see that something will remind me that I made a mistake. You can also consider turning on this DRD enforce off or on. Basically, it's gonna prevent you from making any mistakes. So right now, what I have notify on, meaning that if I make some mistakes, it's gonna show a button like this, like a exclamation mark or some marking like this, telling me that okay, here you made a mistake. But then if I turn this on, it's basically showing that it's just gonna prevent me from doing that mistakes, which I don't really like, but it's up to you. So now that we have these two turned on, we can start doing the layout. So I guess the first thing that we want to do is connecting the bulk and the source of the PMOS. So here, what we'd like to do is, so what I usually like to do is I would go to routing. So now you see that in the routing layer, because right now routing is what we're doing, I would just only leave the useful things on. So here I want to use metal 1 for this connection. Then I would just first select metal 1, and then you see these buttons AV, NV, AS, NS. So this means all visible, and then non-visible. So if I first select something, and then if I click non-visible, it's going to just deselect all the rest, making this thing visible only. But then because we're doing it in this view, right, it's just going to ignore the other non-routing layers and turn off anything but metal 1 for me. So what I would do is, if I just want to make myself clearer, I would go to all used, and then I click on metal 1, and then I do non-visible, and all there is left is just metal 1. Okay, so let's first try this thing out by connecting this and this. So what we do is we can press P, which is path. So here you're creating a path. And if you move it to the point that you want to connect, you want to start the connection, you can just draw it like this, right? So let me show this again. P, and then if you move on it, I haven't clicked anything. If you move on it, this thing is going to light up, and then you press on it, and then you can start drawing this connection. So again, as I said, for F3, you can have the submenus for anything, which can control like width and snap and all these whatnot. But for here, this is just a very simple connection, and we don't need that. And you see, this is the effect of turning on the DRD notify on, right? If I have a connection that is very short, then this min area is going to show me, basically showing that, telling me that, okay, you're doing something on metal 1, but there's a minimal area rule that you need to follow. So if I do this, it's just going to disappear, because now I have this big chunk as metal 1, which doesn't violate anything. So yeah, this seems clear. And I guess to do the same thing, we should connect the bulk and the source of the VSS. So same thing, press P, move it here, click, and then do this connection. And there we go. So everything here is very symmetric, right? And by the way, symmetry is something that layout people should always value, because for a very low parasitic and very good looking layout, it's usually symmetric, especially if your circuit itself is symmetric. In our case, it is, because it's just inverter. So now I have done these previous steps on the metal 1. I can do all visible and take a look at what's left so far. What's left. So right now what we need to do is we need to connect the drain of the PMOS and the drain of this NMOS, basically this thing, right? This out net. So as you see here, if I want to do this connection on metal 1, this gate is actually on my way, right? So what I would need to do is I need to extend this metal a little bit, and then I'll route it down, right? Because if I just route it like this, it's gonna collide, and I'm basically shorting my output to the input, which is definitely not good. So what I would do is I'll need to create a block here, and then extend it, and then do the routing. So for making a connection on any metal, so I previously showed pressing P for making a path. You can also do R. If you press R, it stands for rectangle. You're making a rectangular metal piece, basically, metal sheet. So now I just pressed R. I'll go here. It automatically snaps to this edge, to this corner here, and then I can start making this rectangle. So as you can see, the min area and min width also shows up, which is fine. I would just need to make this my rectangle slightly larger. So here I just made this connection, and which extends this drain of the PMOS to further. And there we go. There's nothing that the DRD is complaining so far, which is good. What I then need to do is, because I want to make the circuit very symmetric with respect to the x-axis, I would also want to do the same thing down here on the NMOS. So you can either just do what I just did. You press R, you can draw the same thing. And then, by the way, R also has an F3, right? That you can either do the net name and size and everything. But even more conveniently, right? Why don't we just copy this thing, this metal chunk that we just made down here, right? So if you press on this rectangle, and then you click on C, right, for copying, you can copy a one instance out, and you can just make another same copy of this, and then I would just use A, right, to align or to connect the rectangle to where I want it to be. And there we go. This looks beautiful. And the last thing we want to do is we just need to do this connection. So here I'm using P again. And if I click on P, and I do this, bam, the connection is made. So it seems that, I would be a little careful about anytime when you try to make a connection and there's only very limited space in between. By the way, if you want to do this ruler thing, you click on K. So click K, and then you can measure anything you want. But looks like the DRD is fine with it, and then we're happy. We don't need to route it even further or anything like that. Okay, so what's next? I guess the last step of the connection that we want to make is for this input. Right? Because as I said, the input, oh, by the way, if I click on something on the schematic, because of the way that we imported the design into layout, it's going to also light up on the layout side, which is very nice. But then, as what I said, because we've previously already merged the gates of the two transistors, we don't actually need to worry about it. But still, right, you need to make the connection somehow to this guy. Let's say when you're implementing this design in some higher level, right, you would need a connection here, and you probably don't want to do it on metal 1. And that's why you have metal 2, metal 3, right? There will be a congestion, and making the routing on a single metal layer is never preferred. It's actually it's a terrible practice. So what now I'm gonna do is I'll show how to do a via first from metal 1 to metal 2, and then we can extend this a little bit, not on metal 1 but on metal 2 instead. Okay, so first thing, as I said, we basically want to make this connection from metal 1 to metal 2, right? So, and if you remember this picture that I showed previously, metal 1 is basically the metal layer that is right adjacent to the transistors. And now we want to jump to metal 2 and then make the connection there, right? So we basically need this thing that connects from metal 1 and metal 2, which is called a VIA. To make this VIA connection, what we can do in Cadence is that we press O. So if we press O, this create VIA thing is going to show up. And you have mode single, stack, auto, fast edit. You can feel free to explore on it, but I'm just going to do a very simple single tab with only one row and one column, so just one thing. And then here, if you see the VIA definition, right, you want to make a connection from metal 1 to metal 2. So you select M1, M2, C, right? Here you see that this thing lights up, and you probably want to place it to the center of your gate tab. So what I would do is, again, I would first hide this, I place it anywhere, and then I use the magical A button, the align button, to line the center of these two. So there you go. We have a connection from metal 1 to metal 2. Metal 2 is shown in this color, and now you see, just because I made a connection just now, previously VIA and metal 2 wasn't showing up, but now they do. Okay, so the last thing we need to do is we extend this a little bit on metal 2, right? So previously, all I have been doing is doing everything on metal 1, right? But then if you want to draw a path or a rectangle on metal 2, you would need to first select this, right? A metal 2. And then you can, right now I'm pressing P, you can make this extension. And so you should double click for making a terminal, right? Because right now this wire goes to nowhere, and if I just tap it once, it's gonna make like a tap here, but then you can go down, go up. So if you want to just terminate it like right here, then you would just need a double tap, and there you go. This connection is made. Okay, now let's take a look at everything together and see if we missed anything. So we have input connected, we have output connected on metal 1. We have the bulk of both the PMOS and NMOS connected. So there you go. This is a beautiful layout of the inverter. But do you guys think have we missed anything? Right? We're actually missing a very important thing, which is how would the system know, right, what these nodes stand for, right? We actually need to make some pins, some labels, or like these guys, to show to the layout that, okay, this is what I want it to be. This is what I want. This is where I want the input to be. And to do that, you need to make a pin. The pins will come very, very important when you later go for LVS, which stands for layout versus schematic check. So basically, after you do layout on any of the blocks, there are two very important checks that you need to perform. One is DRC, which is basically checking with design rule, or what you just drew, is it manufacturable, right? And the second thing is LVS, which basically checks between your layout and your schematic to see if they match, right? If there's a mismatch, right, you probably did something wrong. You probably made an accidental short or something on the layout level. That's gonna screw things up. And in LVS particularly, the pin connection actually matters a lot, right? You have to make the pins correct to make sure that you pass this LVS. And by the way, a Cadence or this layout suite, it does a very, clever way while doing this LVS, layout versus schematic check. It assumes that it doesn't know. Basically, it assumes that the schematic and the layout, they are completely individual, right? So first, it's gonna extract the netlist of this schematic, and then it's gonna separately extract the layout. And then during this check, they're just gonna see if they match each other, right? And that's LVS. This is very clever. It's very error proof, and just kind of like a side note for you guys if you guys are sort of interested. Okay, so now let's start making the pins. So I guess I forgot to say previously that although I mostly rely on the short keys, if you don't remember on any of these short keys, let's say creating a via or a pin or whatever, you can always go to create, right? There's like shape, which stands for R, as you see here, polygon, paths, wiring, and you can go use P, and the pins and labels and vias, everything is here. Same thing as in schematic, right? You have many short keys, but if you don't remember, you can always use create. So here, let's start creating a pin. And what I would do is go here, create, and then pin, or just press P directly. So you see lots of these options, which is fine. You can just once you figure this out, you can just follow what I'm doing here, and if you follow through, then nothing will be wrong. So for terminal names, because we want to create the pin for input, just press it, tap in, and then usually, just for myself, for my sanity, I would also create a label, right? In some technologies, in some process, maybe not in SkyWater's process, creating a label is actually required together with creating a pin. This might not be needed we'll double check with the TAs will double check if creating a label is necessary in this process, but I would actually create a label. And if this is required, you need to go into this option, and then for the heights, we can make a quick estimate, let's say 0.1. And then you can do create label, same as pin, same as pin. If this is needed, you don't, I never try to understand what this does or what's the difference between these. If this creating label is necessary in this process as well, just follow what I'm doing, but I hope it's not necessary. So once you've done that, just press OK, and yeah, this is all configured. Oh, I guess last thing is you want to check if the IO type of the pin that you're trying to draw here matches with the IO type in the schematic. So here, our IO type is an input, so I do it as input, and then I can hide and then start drawing. So one thing that you need to be careful about is which layer that you want to draw the pins and the labels. Right now, I'm selecting metal 2 because this is where the metal that I want to draw it on. Make sure that, by the way, make sure that your pin and your label are confined within this the right metal layer that you're drawing. So I'm just gonna press on it to draw a rectangle, and then because I created pin, after I leave my finger from the mouse, this in is gonna show up, and then I just do this, and then there we go. We have a pin and a layer and a label on this metal 2 layer drawn here. So, but actually this is not the full picture. We actually need to draw this pin and metal layer on the pin and metal layer. Sorry, let me say that again. We need to draw this pin and metal on the pin and metal layer respectively. So what we need to do, because right now we've just drawn it on metal 2, because well, I just did it. I just drew it on metal 2. We need to change the layer setting of this. So what I would do is I press on it, I select everything here. So you see this lights up, right? Because this is a pin. But we need to make sure both of these are in a pin layer or the metal layer, or in a label layer, not in the metal layer. So what we need to do is if you select these, right, and you press Q for the properties, and then you see the attribute here, right? So this pin here, it says layer is metal 2 drawing, and I would just type it in as, because it's a pin, it would need to be in metal 2 pin, and then you do apply. Now it's applied. Same thing for label, right? We want to make sure that it's on actually label layer, so that's what I'm going to do. And there we go. So right now the pin and the label layer are correct. Okay. Make sure that you save things once in a while. What are the other connections that we need to make? Sorry, what are the other pins and labels that we need to make, right? We need to make for VDD, VSS, and out. So let me do this also. So now we know the short key. We can just do create pin VDD. VDD. Options, everything is just memorized, so that's good. And hide. Zoom in here. Draw a rectangle. So as you see here, and because I forgot to change the metal 2 layer here, right? This is still showing up as metal 2, which is fine. We can change this. We'll need to change it anyways to the right label and pin layer. So this is fine. Okay. And see, this thing lights up. This marking you see, and I think we can select it and queue it. You'll see that there's a min area metal 2, right? Because well, I just made this mistake that this is I accidentally drew this in metal 2, which is fine. We just need to select this, right, this pin, and leave the marker. They will disappear, and we'll just change it from metal 2 to metal 1 label for the label, and then for the pin is metal 1 pin. There we go. Yes. And then if you think this thing is too big for you, this VDD is too big for you, just go in here, go into the property, and then change it a little bit. So height is currently 0.1. Let's make it 0.05. There we go. It sits right in. Let's see if this marking disappears. It still doesn't. Oh, min area metal 2. Did I leave any more metal 2s here? This is fine, right? I think this is some residue. So we can just select this marker and we just delete it. This is fine. We can just delete this marking and see if it ever pops up again. I think it's just a remnant of what we previously had. Oh, yes. And some of you may have remembered, I think I also did one thing wrong, which is what is the property of this, right? Is it an input? Is it an output? So here in the schematic, we previously had it as in out, right? Then we also need to follow suit here. So if you go to the properties of the pin and the label, you see the connectivity, the I/O type. We're going to change this to input output. Same thing for the pin, for the label. Okay, this is good because label doesn't seem to have this. Okay, good. Two more things, right? For output, and 2 more pins for output and for the ground. So what I'm going to do is, because I already have this pin on VDD, I could just select this, copy this guy, and move it here. So naturally, an error mark will show up, which is fine because this is not the right thing anyways. We need to change the name here. So if you go to the property again, right, this is ground. We just need to change the name of this. And this is also, again, a beauty of using of having your layout and schematic symmetric, right? So you can just copy everything. It's going to make your life easier. And you see there are no markings. The previous marking disappeared, which is good. Okay, and I bet that previous marking was a shorting marking. Right? It detects that we're shorting ground to VDD because we put the VDD pin over a ground as well. Okay, last thing is the out, which I can also just copy this guy, copy, and you see, so some of these markings are also very self-explanatory. This says min spacing metal 1.14. So this basically shows me a violation. This is the reason. This is why we want to turn these 2 guys on. Okay, so let's just copy this. Or sorry, now that I've just copied this, let me move this on top. Right, anywhere on this is fine. And then we just need to change the name from ground to out. And also make sure that connectivity also changes. We need to change this too because it's output. It's output. Okay, layout as well. Label. So this label doesn't seem to have a name. This is fine. We just need to call it out. Okay, let's see if this is correct. Oh, okay. We haven't selected the ground. Okay. So, oh, sorry. We should change it here. Text is out. Yeah, so don't get confused. Don't get confused between the net name and the text. We actually need the text to be right as well. Okay, so here everything is right. Let's double check. The connectivity here is output, and there are no apparent DRD errors. Yes, everything looks good. So there we go. This is the full layout workflow of the inverter. So next step for us to do is to run DRC and LVS. Make sure that your design passes these 2 checks. I believe, because this is a pretty simple design, I believe my design here should already just pass DRC and LVS. We'll cover this section about how to run LVS and DRC. There are some knobs that you need to tune, some rule files that need to find in the directory, but we'll cover that in a separate video. Again, if you have any questions, feel free to let us TA know. Shashank and Yorgos are your TAs, but you can also feel free to email me at over here, zhl101@ucsd.edu. Thanks everybody. Good luck.